Here we go. And I want us to do a little bit of housekeeping. And first, I just feel like this is a good time to have a little wee bit of a reality check, which is today we are Wednesday of week 6. So things are moving along quite quickly. So let's take a peek here. This is week 6. So remember, lab 1 is due today. We had a 1-week delay. So week 1 or lab 1 is due today. We are going to talk about lab 2. Lab 2 is going to be due next week. So we are sticking with that schedule. Today we're going to talk about the normal distribution. Next week we're going to talk about sampling and sampling distribution. So that's week 7 and your lab 2 is going to be due. And then week 8 is the exam. Okay. So I will provide instructions. I've been going back and forth, and because our class is so late and I want to make sure that you guys have enough time to complete it, I think what I'm going to do is I'm going to make it live early in the morning, and I'm going to send you all a video message that kind of describes what I expect, and you'll have my cell phone number. It's written at the top of the exam. So as you're taking it, if you end up having questions, you can always shoot me a text and I'll answer it. Now, if your question is, what is the answer to number 3? I'm going to reply back with a lovely smiley face because I'm not going to answer that. But if you're like, are you looking for like, multiple, I don't know, like, are you looking for a full answer here, or is it a narrative? Like, when you say explain, what do you mean by explain? Like any question that you would ask me typically in the course of a class, if we were all in person, those are fair game questions. But again, I've just given, so today I gave 3 exams. So it's just like exam week. And I did have a few students who were like, it's virtual, anything goes. And they're like, is this the right answer? I'm also not going to say, yes, it's the right answer. I'm not going to do that. But if you're like, am I on the right track? Like if there was a question that was more theoretical and you're like, am I on the right track thinking about the conceptual view of research? And I'm happy to say, yeah, you're on the right track. You're thinking the right thing. My goal is never for any question to be so esoteric that you guys are banging head against keyboard. That's not the goal at all, especially since you have access to all resources that have been presented in class, lectures, quizzes, labs, all of that. It should be a pretty straightforward exam. Having said that, it's the first time you have an exam with me, so there's a learning curve both ways. So I do really mean it that you guys can reach out to me at any time, and I'll do my best to answer in a way that is helpful to you and yet keeps the integrity of the exam. So any questions about the schedule for the upcoming 2 weeks since we have an exam and all of that?
So I know you were saying that it will go live Wednesday morning. So is it all right if like we start it early and finish it early?
Absolutely. So essentially, instead of me trying to micromanage your time because it's a late class, I'm just going to post it early and it's going to close by end of day. So you will have the entire day. Now, if you don't get to it because your schedule's super busy and the only time you have to take it is 6 p.m., which is our assigned class time, you will have ample time to complete the exam. In fact, it shouldn't take you longer than an hour. Now, having said that, I've certainly noticed, having taught this class in person and online, that people take longer when they take the exam online because you tend to, what I see is people doubt themselves and then they start searching to validate their information. So that searching for information takes a lot longer. Whereas if they just like felt like, hey, this is it, I got to do it and I'm in class, it goes a lot faster. So did that answer your question, Diana?
It did, thank you. I just wanted to make sure that like I wouldn't be doing anything wrong like if I started it early.
No.
That's all.
No, that's totally fine. Totally fine. Okay, any other questions I can help answer? Okay, so that is the schedule. So let's see if I can minimize that. Can you guys still see Course Connect right now? Yes, okay. So lab 1 needed to be submitted here. Looks like most of you have already submitted it. If you're having any issues either in completing the assignment, and I've gotten a few texts and emails that I've tried to respond to. There may have been one that I did not, and I apologize if there's one that I was missing. I just was back-to-back classes. Um, if any of you are like, I don't get this at all, none of the numbers match up, it made sense, I've watched the video, but now I can't figure it out, shoot me a separate email. Don't worry about submitting it right now. We can do something one-on-one tomorrow if we have time, to make sure that you understand how to do it. And if you're like, life got in the way and it's not complete yet, that's fine. Shoot me an email, let me know, and I'm happy to work out some sort of extension if there's a need for that. Okay. Overall, those of you that have completed it, was it pretty straightforward? Okay, my hope was that doing it in class with the two variables would really show you exactly how to do it. And then you just swap one variable and it should be, again, like I said, fairly straightforward. But so I want to spend a few minutes to introduce Lab 2 now so that we don't get sidetracked. So, and you guys see there's some of these that are hidden from students. So this is because it's a professor view. Obviously, you guys don't see the exam yet. Okay, so this is the Lab 2 data set that you will be using. When you open it, you'll see it'll be called Forest Fires data set. I actually have it open already. So I want to show you a little bit about what we'll do. You'll notice that there are 3 columns that are highlighted in yellow, okay? This is an interesting data set. Universities all around the world have available data set that they share for free on very random, and by random, I mean very random information that they've gathered either through their graduate program or undergraduate research. So I have a soft spot for the University of California, Irvine. That's where I got my bachelor's degree. And they happen to have an enormous repository of data sets. Now, there was one that I considered, and it was like wine consumption about women during COVID. And I was like, whoa, give me all this data. And I thought, appropriate for class, maybe not. Let's pick something else. But anyway, all to say, there's lots of interesting data. They have, once we get further in the class, we'll talk about logistical regression, which are predictive measures. You have independent variables that are predictive of some sort of dependent variable. And they have several data sets that would be amazing to do on that include weight, systolic and diastolic pressure, rates of diabetes, like history of diabetes, history of cardiac issues. Anyway, all factors that could be really interesting in terms of the health field and how to do some analysis with that. This one's a little bit more tame. It talks about forest fires in Southern California specifically. There's a lot of data here that we are not going to be using. In fact, your focus will only be on these 3 columns that have been highlighted in yellow. You'll notice that the first one is called temperature in Celsius. The next one is the relative humidity in percentage. And the last one is the wind speed in kilometer per hour, okay? I actually forget what some of these mean. So this is the amount of rain they received. This is a faulty piece of data they even admitted to. It's the area that burnt, it's all 0. So that's not right. The day the fire started, the month the fire started. So there's interesting data that we could, like different analysis we could do with that as to whether there's a greater incidence if you did a frequency as to when fires occurred. It would likely be in the late summer, early fall months when things are really, really hot and extremely dry because rainfall is low in Southern California. But, you can see there's some outliers. There's a few here in March, obviously, as well. Anyway, we're not going to go and do that. And certainly we're not doing the day of the week the fire started. I think there's some interesting hypotheses that could come out of that. Like, do people mess around on the weekends and start forest fires? Maybe. But anyway, I digress. So the goal for the assignment, and I think I have it written here under Lab 2. Okay, please upload your answers for the analysis of the mean and standard deviation. You should include a table with your response for each sample, along with a couple sentences of interpretation. Okay, so what I'm looking for with this table is that you would have a mean and standard deviation as heading, and then you would have each variable written below it, right? So you would have, let's pull it back up here. You would have temperature, relative humidity, and wind. So it would look something like this. So temp, I'm going to keep the same heading here, RH for relative humidity and wind. And then over here, you will have mean and standard deviation, okay? And then you'll plug in your numbers. You will need to submit this table to me, and then you will give me some sort of interpretive statement about what you're looking at, okay? Now, who remembers how we calculate a mean?
That's where you add up all the numbers and then divide it by how many, like, I don't know the word for it, but like how many like columns essentially there were, like how many different spaces they fill.
Right, the total sample size. Absolutely. Yeah. Or your N. Absolutely. So what we are going to do in class right now is we're going to practice for the category of temperature. Your goal will be to replicate the data that we've just gathered here in this class, replicate the analysis, and then you will run the analysis for relative humidity and for wind on your own. And you will submit to me a table that'll look like this, obviously filled in, not empty, filled in with the data for mean and standard deviation, and then have a couple sentences of interpretation for each. Sound like a plan? Okay, so the first thing I'm going to do is I'm going to select all of this data. So again, this is like my own OCD. I like to just look at what I'm analyzing. So I'm going to copy this data. I'm going to add a tab. And I'm going to call, well, let me just add the data now. Here it is. And I'm going to call this temp. Okay. And then I'm going to take out this because I don't need it to be highlighted in yellow anymore. All right. I'm going to scroll down to the bottom because just like Aaron described, I need to figure out what is my mean. And the way I'm going to do that is I'm going to add up all of this data and divide it by the N. Okay. So my N, don't know who that is this 518, but it's going to be -1 because I've got a heading here. Does that make sense? Okay. Where are we in the world? So it's 517. That's my N. Okay. Now how can I quickly add up the total in that column?
If you highlight the auto sum button.
I love it. I cannot tell who spoke. As somebody who's not on my front page, and it's not because I prefer other people, it just clumps all the people that have their video on at once. But I heard two different responses. I heard somebody say highlight it, and I heard somebody say auto sum. Is that right? So for just funsies, we're going to do it both. So let's do first auto sum, which is right up here under editing. I can click it and it will add up. You can see here row B2 through B518. Okay. And then I'm going to press enter and there's my sum. Now to verify that I did it correctly, I'm going to do the other idea, which was highlight all of them. So scroll, 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 scroll. Okay. And now right at the bottom here, 9765.7, which now question, is that what we got? I don't remember. It should be. Yeah. Do you guys see how those two numbers are the same? 9765.7. So 9,765.7, right? That was doing auto sum. If I highlight them, I already know it's 9765.7. Same thing. Now, this also gives me my count or my N. Now I figured it out because I did 518, right? That was the last cell right here. But I knew there was one that was empty. It was just my title. So I did 518 minus 1, which gave me 517. I highlighted all of them. That gives me a count of 517. So this is part of what I love of math. You can always double check yourself and you see like, oh, okay, the information actually converges. Now, this already gives you your arithmetic average, right? The numerical average, which is 18.89 if you were to round. But let's say I did not know how to do that. What would be the way to find the mean? If I have these two pieces of information, what do I do next?
You divide the sum by the sample size.
Divide the total by the sample size. So we said, Diana? Yep. So I would do equal, open parenthesis, 9,765.7 divided by 517. Close the parenthesis, 18.889, just like I got earlier. Okay, now notice here in my formula, I didn't say divide by B 520. I didn't highlight the cell. Why is that? I just want to point out a common error, okay? If I were to do that, let's take this out and instead click this. Look what happens. It's throwing me an error, okay? Now, if I'm like, well, what's wrong? This was the perfect thing. I divided by n. I can click this right here, and it says a value used in the formula is of the wrong data type. You guys see that? Why is that? What's wrong with row B520?
Is it because like 520 says n equals and like that's the sample size versus like everything else, which is like part of the data set?
That's exactly right. So in one cell, I have a combination of letters and numbers. And Excel is pretty simplistic in terms of doing formulas. It needs only numbers, okay? So if I wanted to fix that, I could go here and take out n equals, right? Just leave it 517. And then over here, I could do n equals. And now we are back in business, okay? I want to show you guys this because this is a common error that you guys may run through and you're like, she was doing it and it was working just fine. And now I'm doing it and that's not working. And it's nothing as frustrating as that, especially when it's something that's simple. Okay. So if you're using a formula and you are selecting a cell, make sure that cell only has numbers and not a combination of letters and numbers. Okay. So let's go back to our original tab. I'm looking for mean and standard deviation. I believe I've just got the mean. I'm going to round this. If I want to, I can right click, format cell, and I'm going to pick number with just 2 decimal. And that rounds to 18.89. So I'm going to plug this in right here. Okay. The mean for temperature, 18.89. Okay, now how do I do a standard deviation? What's the first step? Aaron's digging deep. I can tell. He's like, she talked about it last week. I think we practiced.
I'm trying to remember without looking at my notes. And it's just,
Valiant effort.
I just remember there's like a lot that goes into it.
Yes, that is correct. Doing the standard deviation does. All right, so the first step is I want to take each value and take it away from the mean, right? So I'm going to do x minus the mean, okay? Or x minus x bar, right? The bar on top of the x. Okay, so the way I do that is press equal, open parenthesis, select the value, right? Select the specific cell I'm looking to use. My x here is 8.2 minus the mean. The mean is 18.89. Close parenthesis, enter, negative 10.69. Okay, I'm gonna do it for one more. Equal, open parenthesis. I select the value next to it, B3, which happens to be 18, minus my mean, which is 18.89. Close the parenthesis, enter. Here I am at negative 0.89. Now, what did we learn about Excel that was kind of cool last week? Do I have to keep doing that for all 517?
No, there's some like function you put in that will automatically do all of them.
Right. How do I do that? You guys remember?
If you click on the bottom corner of like the second line, the square will come up, and then you click it.
You're a little glitchy, Diana, so I didn't hear all that, but I'm pretty sure you were saying the bottom one has a little square on it. You grab it once you get the little crossbow or a target sign, click it and drag all the way down. All the way down till 518. Here we go. Right here. You let it go and it populates. Okay. What is the next step?
Multiply each one by themselves.
Yes. So now we are doing x minus the mean squared. Okay. So what I'm doing now is equal, open parenthesis, cell C2 times itself, close parenthesis. I'm going to do it for one more. Equal, open parenthesis, cell C3 times itself, close the parenthesis, and here we go. Now, I know the trick. I'm going to highlight it, grab the little crosshair, that little square at the bottom, turns into a plus sign. I click and hold all the way down. So right here, I let it go, and it auto-populates. All right, what is the next step?
Add all of them up.
Add all of them up. So again, I'm going to click this cell right below. I'm going to go up to auto sum. Click that. Press enter. Here we go. 17,397.92, we'll say. Okay. Am I done? No. What do I need to do next?
You have to divide by the total number minus 1, right?
We're so close.
Oh,
yes. No. Did we do -1 or just minus the number? For variance. Anybody else want to pipe up?
Okay, sorry, what was that?
No, and again, Aaron and Diana, you guys rocking it. You're answering all the questions, so we can let some other folks pipe up here. Do we divide it by n or n minus 1? It glitched and I didn't hear what you guys thought.
N-1.
N-1. Okay. And what does that look like? So I can grab this number. Oh, did someone answer too? N-1. Good job. So I'm going to be right here. This is going to calculate my variance. Okay. So I'm going to grab the total. This is the sum of the difference between X minus the mean squared. Here's my value. I'm going to divide it by, and I'm going to open the parenthesis, this 517 minus 1. Close that parenthesis, close the other parenthesis. Press enter. 33.71. These things are obnoxious to me, so I'm going to format the cell, make it just 2 number. Oh, 33.72. So much easier to look at. All right. But now over here, am I asking for variance? No, I'm asking for standard deviation. So how do I get the standard deviation?
Square root the variance.
Square root the variance. Okay. So remember, there's a cool way if I press equal and I can start typing in square root, SQ. You see the very first function is square root, returns the square root of a number. I'm going to click that. I'm going to click the number and I'm going to close the parenthesis and press enter. Boom. Standard deviation of 5.81. Okay. Now I can go back over here, fill this in. Okay, now we know how to do it. We saw there was like a trick to getting it so that you can have your mean right away if you just highlight it. Let's see how we could do standard deviation for a sample right here. Estimates the standard deviation based on a sample. So again, this is a function. So I did equal ST for the start of standard deviation. Now I'm going to double click on this and it tells me to highlight a sample. I'm going to highlight this sample starting over here all the way to the top just to verify my numbers. Just a good feeling that we're all on the same page. I'm going to close the parenthesis. Press enter, 5.81. Okay. Now, perhaps some of you are like, why did we spend the last 25 minutes of class going through each column and adding it? This was nonsense. Well, that's because if we were in class, we would actually be doing it by hand with a calculator. So first of all, thank our lucky stars, we can use Excel and its formulas. But it's good for you guys to know how we get the numbers, right? How did we obtain that? Sure, you can just click a button and it gives it right back to you. But isn't it satisfying to get the double checking of like, yes, we nailed this. So that is the way you would get the standard deviation. So I can go back over here. Now I have filled in the section for temp. Your lab that is due next week is to do the exact same thing I just did, but do it for relative humidity and for wind in kilometers per hour. Okay. Once you're done with your analysis, now, if I were you in your shoes, this is how I would do it. I would download the file. I would create separate tabs for each of them. That's just how my brain goes. You don't need to do that. That's just, I like things neat. And then I would have this exact setup for each variable, okay, where you know what you're doing for each. And at the bottom, you've neatly labeled everything so that you know exactly, you know, like I could have this even highlighted so that I know those are the two values that I'm bringing over into this. What you are submitting to me is this table along with a couple of sentences of interpretation. Now, here's what it would look like for temperature. Based on the data gathered in Southern California with forest fires, the average temperature where a forest fire occurred was 18.89 Celsius with a standard deviation of 5.8 degrees. Okay. This tells us it has to be pretty hot in order for there to be a fire in Southern California. You guys can even transfer it if you want in Fahrenheit, so you know what that's like if you're not familiar with Celsius. Okay, questions as to how I got here? Does that all make sense? Like, bring it. We got this. Okay. So lab next week, again, you are highlighting this table. You can copy it in a Word document. You can send me all of this data set if you want. That's fine. As long as below you have a few sentences of interpretation for each of the variable. Okay? All right. So that is lab 2. You will see it's right here. Oops. You need to turn it in by next week. Okay. Now, actually, what we are talking about today is normal distribution. Do I have it open? Nope, that's another class. Let's open it right now. Can you guys see it or no? Probably can, huh? No.
Oh, there we go.
Now you see it. Okay. All right, so normal distribution. When you hear that, what do you guys think of? Anything
like
come to mind?
Factoring almost.
Factoring? How do you mean by factoring?
Like a lot of variables like 5x minus 2 in parentheses times 14x plus 72 in parentheses. And then you got to like kind of distribute everything.
Oh, I love it. I'm about to make your night, Aaron. Normal distribution, way simpler than that. Because yes, you're right. That's like distributing for algebra. Whew, we are not doing that. So a normal distribution is, in most social sciences, when we talk about data set, we make an assumption that it is normally distributed. For instance, for this class, the dean might come in and go, obviously in Dr. Woltel's class, there's a normal distribution in terms of scores. We have a very small number that's getting an F, probably a small number that's getting an A, with most people centrally, right, central theorem, that are centered around the middle, close to a C+, right? That would be a normal distribution. All right, so let's talk about what it looks like. So specifically in this chapter, we'll talk about the importance and why we use a normal distribution. We'll talk about the properties that are known as far as a normal distribution. Specifically, it's known usually as a bell curve. Maybe that's another way that you've heard about it. And then we're going to figure out how to transform a raw score into a z-score, and then flip it back around, how to transform a z-score back into a raw score. We're going to talk about what is a z-score in comparison to a percentage, and lastly, how to calculate and interpret percentile ranks of a score. To be honest, this is a meaty lecture with more math, still not as complicated as the math Aaron was suspecting. So, hey, kudos to that. So we may take a break and then we will cover it again next week because I want to make sure everybody's on the same page. Z-scores are a classic stats thing that you need to know. So I would rather cover it a little bit more so that everybody's set up for success for the exam. Okay. So again, a normal distribution is a bell shape. So it looks a little bit like this, right? Looks kind of like a bell. Okay. It is symmetrical, meaning if you cut it in half like this, it's about the same amount this way as it is this way. Okay. So it is symmetrical about the mean. And then it usually, this point, this apex, it combines all of them. The mean, median, and mode all coincide at this peak, at the very top of the bell curve. And the frequencies are gradually decreasing on both sides. Okay. So again, your mean, median, and mode are all equal. So that is for a normal distribution. It is a theoretically ideal distribution, which means in the real world, unless you have a massive sample, it usually does not mimic a perfectly normal distribution. Let's take height, for example, okay? If you guys thought of every person you knew and jotted down their height, or actually, let's do it for this class. In the chat, or just say it verbally, what is your height in inches? Like, don't tell me 62 inches. I'm not gonna know what that is, but like, so I'll start. I am 5'6". Oh boy, I'm not good at drawing. Okay, 5'6". All right. So we've got whoops. Oh, it's not gonna let me do that. Let's see. Oh, it's still not. Okay. 5'4", 5'2". Somebody's gonna need to say it out loud to me in the chat. Somehow it's not letting me do both. 5'4", 5'2".
Is next.
5'1", 5'10". 5'10". Okay.
5'3",
5'3",
5'9",
5'9",
5'5",
5'5".
5'6", 5'9", and then 5'7".
Thank you so much. I don't know who that was, but I appreciate that. Was that Liz? Thank
Yeah.
you. Okay, so 11. Somebody didn't answer. Is there one more? We've got somebody in the class not necessarily paying attention. Okay, so all right, let's test that out. What is my lowest score?
5-1.
5'1". Okay, right here. Highest score.
5'10".
5'10". Okay, somebody else. Wait, Hasher, had you already said 5'10"? Or Aaron, was that you at 5'10"? Look at me making assumptions about the guys being the tallest. Hello, Dr. Woltill, gender stereotype.
I mean, I said 5'10" too, but it looks like Hasher did as well.
Okay, so maybe Hasher he was our missing number. Okay, so let's go back here and add one more. 5'10".
I already said 5'10".
Okay, well, we should have two 5'10s, right? Okay.
Oh yeah, we're both in there.
Yeah, okay, 5'10". Sweet. All right, now looking at this, does
Yeah.
this, what's that?
Oh, I'm sorry.
No, you're good. All right, so if I wanted to do a normal distribution, what is the first thing I would need to know? So if I know that a normal distribution, right? I need to know the mean, right? Because I know that the mean, mode, and median are all the same and it's at this apex. Okay, so my range is 5'1" to 5'10". We can do some quick conversion here. Bust out your calculators. All right, so 5 foot is 60 inches, right? Right? 5 times 12. Okay, so then figure out each of these. So whoops. All right, do over. All right. So the way we calculate the mean is we know that 5 foot is 60 inches. So like this is 66, 64, 62, 61, 70, so on and so forth, right? So you add all these guys up and there are 12 entries. So then I take my total divided by 12 to get my mean. What number did we get?
I got 65.66 repetition.
65.6?
Yeah.
I got 66 even. Anybody else get that? What do people get?
I got 66.083 with the 3 repeating.
I'm getting a couple more responses here. I'm redoing it as we speak, just to make sure I'm not. Anybody else?
I got the same as Hannah.
66.08.
Yeah, with like the 3 repeating.
Okay.
I got 66 even as well as you.
Okay.
I got 66.
Okay. Let's go with 66. Just for the sake of simpleness, because it's not even a round number. All right. So 66 too. Okay. So we'll say, whoops, 66. So this is actually 5 foot 6 inches. Okay. Now I would need to be able to do a standard deviation, right? Which we could do real quick on this one. But ultimately, in order to have a normal distribution, that would mean that the scores are going evenly down on either side, okay? Let's just look at this. This would be 67, 68, 69, 70. This would be 65, 64, 63, 62, and here's 61, okay? Now this tracks, we have 1 at 61, 1 at 62, 1 at 63, 1 at 64. I think we only have 1 at 65. We have 2 at 66. Please correct me if I'm wrong, because I'm kind of looking through this, just eyeballing it. 1 at 67. We have 0 at 68. But then here we have 2 at 69, and we have 2 at 70. Okay. So in fact, I'm making this fit a normal distribution. This is really the distribution of height of our class. It's 1, 1, 1, 2, 2, 2. You guys see that? So this here is 5, 6. In fact, there's probably like, let's make it even better. Because this is 1, 1, 1 for 5, 1, 5, 2, 5, 3, 0 for 5, 4, 0, so 1 for 5, 5, 2 for 5, 6, only 1 for 5, 7, 0 for 5, 8, and then we go back to 2 for 5, 9, 2 for 5, 10. Do you guys see that? So ignore that. In other words, in our class, is height normally distributed? Does height follow this pattern of a bell curve? No, it does not. Not even close. Okay. So why is that? Well, because this is called real life, right? Real life very rarely matches up to a theoretical abstract. Okay. In fact, if we were to pull out the guys here, which both guys were 5'10", the average height of a woman in the US, I think, is like 5'3", 5'2". So even that, we're like way skewed tall. So again, it's a theory. A normal curve is a theory. It is not based on real life. And how large is our sample? Our class has 12 people. Is that what it would be considered a large sample? No, not at all. Now, if you randomly selected 200 people in Grand Rapids, you would probably get pretty close to a normal curve. Now, would it match the US curve? No, because this is like mostly Dutch land and everybody's a giant here. When I first moved, I was like, what is happening? Does everyone play basketball here? I don't understand. You're all so tall. I tease here, not trying to start anything, but yeah. So the greater your sample size, the greater it'll approximate the theory, but it is still a theory. Normal distribution is not perfect. Okay. So here are some common characteristics. It is symmetrical, it is unimodal, it only has one apex, and most scores fall near the center and very few at the extremes. So it truly does follow this kind of pattern, right? Where you've got one apex, only one mode, and then most scores fall in this region right here, and very few are at the tails or the extremes. This is what it looks like, much nicer than my chicken scratch. Okay, and you can see again on this, the mean, median, and mode are all centered around the same number. Okay, so again, you wouldn't have an instance like we had in our distribution where the same number of people had the same height all throughout, like 5'6", 5'9", and 5'10", all doubling up. Okay, that wouldn't happen in a normal curve. Okay, this is the nomenclature or the way you'll see the symbols written for population and for sample in regards to mean and standard deviation. If you are dealing with an entire population, you will see mean is noted as the Greek letter mu. Okay, now quick refresher. When would you see, or what would be an example of a population?
College, maybe?
Like all students at Aquinas?
Like students who like commute to Aquinas or students who don't.
Okay, so actually, and I hate that I cannot tell who's talking. Was
It's
that Grace?
Grace, yeah.
Okay, sorry, Grace. So that would actually be a good example of a sample, because if you're looking at students who commute, you are taking a subset of all of the population of Aquinas students. So so it'd be like saying in the US, how many people drive a car? Well, it's a sample. You're taking a subset of the entire population of the United States. Okay. Think population is census. You are counting and including every single person within a certain domain. So if you wanted to use college as an example, it would be all students at Aquinas, everyone at Aquinas. That is the population. Okay. Or all people in the US. So absolutely. That is a population. You're counting every single one of them. I want to know about the reliability of Hondas. I am including all Hondas, all of them together. If I'm interested in the reliability of the Honda minivan, now I'm taking a subset of it. I'm just looking at minivans. Okay, you can tell what I drive. That's fancy pants over here. So that is how you would notate the mean for a population. For a standard deviation, it's the Greek letter sigma. So it's like a circle with a little tail on it. Now, if you're doing a sample, it's usually notated as a capital italicized M, and the standard deviation is SD. I will say that very often you will also see it as an X with a bar on top, and the standard deviation will be a lowercase s. Sometimes it's italicized also. And this is how you would see variance, because truthfully, that is what variance is in comparison to standard deviation. It's standard deviation squared, right? Because in order to get standard deviation, you just take the square root of the variance. So you can think about it backwards that way. All right, we talked about this, I want to say a little bit last week when we were talking about central limit theorem. And it's the idea that if you're taking an entire, whatever sample that's fitting a normal curve, 68% of the scores will fall within one standard deviation of the mean. Okay. So if I get my mean, let's say it's height again, and I discovered that the mean height for individuals in Grand Rapids is 5'7", okay? And my standard deviation is 1 inch, okay? So that means 68% of the population would be between 5'8" and 5'6", okay? If my standard deviation is 1 inch and my mean is 5'7", or 67 inches, then 68% of the population falls within one standard deviation of the mean. So it's one standard deviation below the mean and one standard deviation above the mean. So that would be 5'8" to 5'6" would be 68% of the population. Now, if I take it over to one other standard deviation, so now I'm 2 standard deviations away, that's 95% of my population falls in that range. So for my example, random example of height, if this is again 5'7", then I'm looking at 5'5" to 5'9". That range will have 95% of my data will fall right in that range within 2 standard deviation of the mean. Okay. And lastly, if I go up to 3 standard deviation away from the mean, right here, that's 99% of my population falls within that range. Okay, let's use a slightly different example. IQ, that's something you guys probably hear about. Anybody offhand know the mean IQ score? Random person you pick, you do an IQ test, what would be their IQ? If you guys don't know, that's totally fine. I don't know if that's something you guys cover in Intro to Psych.
I just looked it up and it says 100.
That's correct. It is 100. You will likely find that the standard deviation is 15. Okay. So that means most people, if you take an IQ test, the mean, and let me erase this nonsense here so that, okay. So if I am calculating IQ, this is 100. Now, what are if the standard deviation is 15, what are the scores for one standard deviation below and above the mean?
$85 to 115.
Okay, good. Does everybody see how Diana got that? If I know, oops, looks like somebody got kicked out. If I know that my standard deviation is 15, then I take my mean and I add 15 to it, and that gives me the point for right here, for one standard deviation above the mean. And I do the same thing the other way around. I take away 15 from my mean, so that gives me 85. Okay. Now, 68% of people, if they're taking an IQ test, their score will range between 85 to 115. That is actually what's considered the average range, okay? Now, if I go one standard deviation above, what would be this 2 standard deviation? What are the scores here? What do we think?
So, wow. Okay, so wow, I'm at a loss for words. 85 minus, so bottom one's 60, right?
Close. 70.
Oh no. Oh my gosh. Okay. And then the top one's 130.
Good. Okay.
I struggled so hard trying to find 85 minus 15.
That's fine. All right, let's take it one step further. 70 minus 15,
55.
55. Okay. This 130 plus 15, we're at 145. Okay. This is where it gets real fun, gang. Okay. Now, let's say you are like, I'm a rock star. I'm the top of the top of the top. I scored 116 on my IQ test. Right? Let's say one of your buddies is like totally venting, like, or not venting, but they're like, not, what is that called? Like boasting. They're like, they think they're amazing at 116. They're like, I'm like better than like the entire world. I'm amazing. How could you pop their bubble based on this? Where would they fall? Gloating. Thank you, Stephanie. That's the word I was actually looking for. Yeah. So
It's okay. I'm a mind reader. I know.
okay. So 116, where does their score fall, right? If we know that 68% of a population or of scores will fall within one standard deviation of the mean, if they fall in this quadrant right here, which 116 would, how would I calculate what area they would fall into?
I'm probably gonna say this like in a really like incorrect way, but you'd add like 68% to 13.6, 2.13, and then below that. Or you could say like what's above their number and then like describe that there's like that much percentage above them.
Very good. You're very much on the right track. Now, without doing z-scores, I can't give an exact percentage. But if I know that their score falls somewhere in here, I can add all of this right here and say that they are above that. Because now let's add all this up. If I add up all these percentages, that adds up to 100. Okay. So if you think about doing percentiles, you're doing a rank score out of 100. So absolutely, Diana's right. They are above the 68%, right? They fall like right above it. So the way I would do is I would take the 68.26 and then I would add this part and add this part because it's saying their score is above all of these people, okay? So it'd be 68.26 plus 13.6 plus 2.13, which eyeballing it, that'll probably be about like 85, 86% or so. Does that sound right? Okay. So that's one way to do it. The other way I can do it is say, okay, yeah, they're better than all of this area. Here, let me shade it in now. Okay. They're better than all of this, right? So they're shoop, 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 all the way up to here. So really, I just want to know if I'm curious as to like what top, they're in the top what percentage. I'm really just interested in adding these two values right here. Okay. So 13.6 plus 2.13 gives me what, 15.73? So I could say they're in the top 15.73%. You guys see how I did that? Or you can flip it on its head and say that they are better than 85, whatever this percent, like if I add all this up. Or you could do 100 minus 15.7. So what is that? 84.27. Okay, is this making sense what I'm doing? Okay, this is the baby steps that's getting us towards z-scores and changing it into percentiles. You will need to know the distribution, the percentage under a normal curve. Okay, I did a lot of chicken scratch on here, but ultimately what you need to know, in fact, let me just do this so that you need to know these numbers. That's what's most important, okay? All right. Here it is again, in case we got confused. So a normal curve and the percentage of scores between each mean. Now, this is the same thing. We just simplified it and just made it straight percentage, 34, 14, and 2%. Now notice here, these are z-scores. Okay, that is a way that we have transformed raw scores into a standardized format. Okay, you can always compare z-scores. So you would be able to compare someone's score on an IQ test and their shoe size if you had it in z-scores, right? Because you're not caring about the unit of measurement. You have a standardized measure. We'll talk about that again in a second. But the idea here is that this follows the exact same distribution as a normal curve with a z-curve. Okay. This is exactly what I was talking about. So knowing one score tells us very little as to how it relates to a whole distribution of scores, okay? If I tell you that my score on a leadership scale was 92, you might go, oh, all right. What is it out of? Is it out of 100? What is the mean? What does it mean actually that you would get a 92? I just made up a number, right? Like, is that meaningful? Or if somebody told you, I weigh 130 pounds, and you're like, okay, are you 4'2"? Are you 8 foot tall, right? Those other factors are going to have an impact, right? So knowing one number in the absence of the distribution it's in lacks meaning. It is hard for us to interpret. It's hard for us to make any sense of it. Okay. Well, as soon as you have a measure of central tendency, like a mean, you're able to see if the score falls above or below average within that distribution. Okay. Knowing again the standard deviation on top of it indicates how much above and how much below the mean is your score in comparison to the distribution as a whole. That is why we cover mean and standard deviation, because those are huge. We really need those to fully grasp the impact of the score. Okay, so this is the score of one student, Jerome, in relation to the overall distribution on the measure of the extent to which students are morning people. Okay, so the mean, let me put my laser pointer because I'm having a hard time seeing. The mean is 3.40. You see, this is one standard deviation above is 4.87, and Jerome's score is a 5. How would you interpret Jerome's score in terms of the extent to which he is a morning person? And if you're talking, you're muted, my friend.
Oh no, sorry, I had to use the bathroom, so I was just trying to catch up real fast.
Oh no, it's totally fine. I could see that you were mouthing, and I was like, oh gosh, if he thinks he's talking, we can't hear him. Okay, Hasher said he's pretty much a big morning guy given where he falls on the line. Excellent. That's exactly what it means. So if the mean as to how much they're a morning person is 3.40, he is over one standard deviation above the mean. Okay. This is interesting to me. Just either raise your hand in the Zoom or say me. Would you consider yourself a morning person? Yes, no? Yes? No to Hannah. Medium for Diana. Liz says no. Yes, Stephanie. Depends on the day, Hesher. That is some truth right there. Camilla, depends. No, not really. Okay. I feel like in college, I was not a morning person. I was like, is it 3 a.m.? I can't tell. I'm not even tired. Definitely a night owl. Now that I am old, I love being the first one up, waking up. I mean, for a while, I was waking up at 4 in the morning. That was delightful. Just do dishes. Yep, not a morning person. I get that. Okay, this is kind of interesting. Random musings. Okay. Now, what is a z-score? Let's dive right in. It is a number of standard deviations that a given score is above or below the mean of a distribution. A z-score is used to standardize any type of raw scores. It could be miles, seconds, pounds, percentage, calories, really anything that you can measure, any interval ratio item that you are able to measure can be turned into a z-score, okay? And its goal is to show you where it falls on a normal distribution. Now, we just talked about how common is a normal distribution in everyday life if you're to gather data. Very rare. But if you kind of push the data in that direction and you transform it to fit a z-score, you are able to get more meaningful data from it. And now you're able to compare things that in the past you wouldn't be able to compare to, right? If somebody told you, I weigh 150 pounds and I'm 5'9", and then they ask you, am I average? You're like, you're talking about different things here. I don't know what to tell you. If you put it all on a z-score, you're able to see if they're above average in each. You're able to speak eloquently about it, okay? It's a measure of standardization. Okay. So here it is again. This is the same scale we looked at earlier. Your mean ends up being a z-score of 0, okay? The mean is always going to be 0. One standard deviation is just 1, okay? So no matter what the standard deviation is, in this case, it's 1.93, or no, that's not true. It's 3.40 minus 1.93, so it's like 1.57-ish. It's always a measure of 1 for z-scores. It's really clean and simple, okay? So you can see again, this is the raw score. We've just transformed it to this z-score where the mean is a 0 and with each standard deviation is just 1 or 2, 3, 4 as you go through with standard deviations. So this is the number of times each hour that 2 children spoke, shown as both raw scores and z-scores, okay? Now, what is this area, or what is this value right here?
The median.
So close, Hannah, so close.
The mean.
The mean, you got it, the mean, yes. And I know that it's the mean because the z-score is 0. That's my ding, 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 ding moment. That's got to be the mean, okay? Now, how's Jacob do?
Kind of below average, essentially.
Yeah, he's 1 standard deviation below the mean. Absolutely. How about Ryan?
He's above by 2 standard deviations.
Yeah. Ryan's probably getting in a lot of trouble, gang. Let's just be real here. He's a chatterbox. He should be Chatty Cathy. That should be his name. He can't stop talking. He's way above average, okay? This is how much these 2 boys talk per hour, okay? All right. Again, if you're just given the number of times they're spoken, like that, the raw score, it's like, I don't know, he got a 20. Is that a lot? I don't know. I could do some math real quick and tell you how far it is. But if you just see, oh, he got a z-score of 2, right away, you know, that's 2 standard deviations above the mean. Yeah, that's significant. That dude's a talker. All right. Now, this is how we will calculate the z-score. It is the number of standard deviations that a given raw score is above or below the mean, okay? So if I take a peek here, this is what it's like. This is the basic, formula in your textbook. It has like this. It's big on the Y bar. I don't know why it does that. But a z-score is your x, your actual value, right? Your raw score minus the mean divided by the standard deviation. Okay. Now let's say you don't have a raw score, you just have the z-score. You can transform it the other way. You can get back to your raw score by inserting your z-score times the standard deviation plus the mean, and that'll give you your raw score. It's just transforming the formula around. Occasionally, that'll be helpful. Okay, here are some scores on the SAT. Again, this is back 2014, 2015. Let me switch it to this real quick. Okay, so this is the number of test takers, 1.1 million. Okay, so already I know this is going to be pretty much a normal distribution. The sample is massive, okay? The mean for critical reading was 485 with a standard deviation of 110. Math was a mean of 501, standard deviation of 117. And writing was a mean of 475, standard deviation of 109. Okay, let's break this down. If I am looking for the z-score specifically for this random number, right? So here I am at 584, but I'm comparing it, I think that's writing. Yes, that's the mean for writing. I would take my score, 584, this is for writing. This is my raw score, 584 minus the mean, which is 475, divided by the standard deviation, which is 109. And that gives me a score, a z-score of 1. What does that mean? How did this student do?
The student scored one standard deviation above mean.
Yes. Okay, this is what I would hope all of you guys would do. If you get a positive number, go back and double check. Okay, my original score was 584, which I know because I, graduated kindergarten. That number is bigger than this number, so it makes sense that this student scored above the mean, right? Occasionally, I'll get students make it an arithmetic error and they just look at the final value to make all their interpretation. They don't take a step back to go, wait. I'm saying this person is worse than the mean. That doesn't make sense. This number is higher. I must have done something wrong with my math. So I recommend that you guys always double check what you do. Okay. So this is one standard deviation above the mean. Now let's say a different student scored a 366 on the writing score. I would do the exact same computation. 366 minus 475, which is my mean, divided by 109, which is my standard deviation, gives me a score of -1. That tells me the student scored 1 standard deviation below the mean. Okay, so they did worse than most. Any questions about how to manipulate the formula? Is this pretty straightforward or questions about it? This makes sense? Because we do nothing but build on this. So if it's not making sense right now, stop me. I want to make sure that it's clear. Okay. Shoot me an email or a text if you're like, I don't get it, but I'm embarrassed. Just first off, never be embarrassed. If you have a question, there's probably 20 of you that, well, this is a small class, but 2 others of you that have a question. Okay, so this is the standard normal distribution. This is for the same test. This is the writing test on the SAT. Right away, I know that this is my mean because here is my z-score of 0. That's indicative of the mean. And then I can see this is -1, -2, -3. And you can see they just dropped the scores. Now they gave us that the standard deviation is 109. I could just do 109 minus 475, so on and so forth. This would be the standard normal distribution for the Z scores for the writing test of the SATs. Okay, let's talk about some properties of z-scores. So first, the sum of a set of z-scores is always going to be 0, okay? And the reason why that is because it's each value is the mean has been subtracted from each score. So following the definition of the mean as a balance point, the sum and average of the deviation scores must also be 0. Okay, that's just a general property of a z-score. 2, the standard deviation of a set of z-scores is always 1 because the deviation scores have been divided by the standard deviation. Okay. And lastly, z-scores follow the same distribution pattern as the original raw scores. So, in other words, if the original distribution is skewed, the z-scores are also going to be skewed. Z-scores are standardized, but sometimes they're only called standard scores when they follow a normal distribution. And lastly, when the normal distribution is represented by z-score, it's called the standard normal distribution. Okay, let's be real here. Am I going to be asking you questions like, and what was the second? No, I'm not going to do that. That's dumb and no one should be doing that. This is just some basic knowledge you guys need to have about z-score so that it makes more sense to you. Why do we standardize it? Why do we do it? Okay. The standard normal distribution is another word that will be used for a normal distribution or for a z-curve. So I just want you guys to be familiar with that. So if you see that term somewhere else, you're not like, I have never heard of a standard normal distribution. Dr. Woltell ripped me of my education of statistical knowledge. Now it's written right there. It's interchangeable. If you see it somewhere else, it means the same thing, just different word for it. Okay, so these are the properties. All right. Now, let's talk a little bit more about the normal curve table and z-scores. Now, how many of you guys have the textbook for our class?
Me.
My hope is that most of you do, but if you don't, I get it. Textbooks are super expensive, and I'm sure you're like, do I need another door stop in my dorm room? I don't know, maybe, maybe not. Because after this class, it may be a while, gang, before you use it again, because most of you are what, sophomores, juniors? If you go to grad school, they will give you a way more expensive text to buy. Just dropping down some truth here. They're going to have you pay for another one that'll be triple the price. But if you have the textbook, that is lovely, because there is at the very back of it in the appendix, you will see there is a normal distribution and z-scores. The table will have all of the values written, okay? It shows the precise percentage of scores between the mean and any other z-scores. So remember what I did earlier, and I said the IQ was 116, which was right above that average piece. And I'm like, if we just eyeballed it, what would be the percentage? It was just that, we eyeballed it, right? We could say with a fair amount of certainty that that student was in the top 15% of the distribution, right? But I couldn't say that student was in the 15.7th percentile. I couldn't say that because I was just kind of eyeballing it. The charts that you have at the back of your book, and what I'll talk about in just a minute, will have the precise number of what is the area underneath the curve, underneath the normal curve, so that you can see exactly where that score places. Now, if you're like dripping sweat going, I didn't purchase the book and now I'm going to fail the class, don't worry. During the exam, I will include a copy of the appendix or a copy of a z-score. Because let's face it, statistics, this is the other part that's lovely about math, it doesn't change, right? It's pretty constant. So you can Google on the interwebs z-score distribution, and you will find like 10,000 of these sheets that have the exact same information underneath it. So do not panic. Okay, so let's talk about that, the sheets you will find and what's in the appendix of your textbook. It will show the precise percentage, again, of scores between the mean and the z-score. It'll include also the precise percentage of scores in the tail of the distribution. And you need to know it only lists positive z-scores. So if you have a negative z-score, we'll talk about it in just a minute, but use your brain is what I want to tell you. Okay, and I'll show you why in just a minute. Oops, that didn't work. Here it goes. Okay, it'll look something like this. So in your textbook, it's table 3.1. This is within the chapter for, I think this is chapter 4, 5 we're in. I could be wrong about that. It's in your, might be chapter 3. That might make more sense. But the appendix in your textbook will have this table A1 that will have exactly this information. So let's get oriented to this a little bit. The z-score is going to be written right here. Okay. And then you'll see the percentage of mean to z. Okay. This is this section. So notice these are all positive z-scores. So obviously z is going to be on this side because negative z-scores are on that side. Okay. These are all positives. It's going to be over here. And this is the percentage that is from the mean to your z-score. Now let's have a quick, let's make sure we're on the same page moment. Whoops, that's not what I wanted. What is the percentage of the distribution that falls in this shaded area, what I'm shading here?
%50.
This is 50%. Yes, very good, Diana. Okay, how did Diana know this?
Because
Is it
it's
just 'cause it's half?
Because it's half, right? One of the very first slides of today's presentation stated, if you have a normal distribution, it is perfectly symmetrical. If you cut it in half, you have exactly half on this side, half on that side, right? So, and I know it's cut right at half by the mean. The mean is the apex, it's the central number, okay? So 50% of my distribution is right here. Now, if I'm looking at the percentage of the mean to z, and the question is, this student scored at this value. Here was the z value. Let's say it's 0.64, okay? Out of 100 students, how many did he beat out, right? Or what would be the percentile of this student? Do not just answer 23.89, right? Because 23.89 is bitty, right? And if we know this is a score that's above the mean, what do I need to do to this number?
Add it to 50%.
Add 50% to it. Yes. So this needs to be plus 50. Okay. So this would be 73.89. So if I'm looking at a percentile, this score would be in the 73rd percentile. Okay, we'll talk about that in just a minute, but I just want you guys to reason through it, right? If it's positive, I'm looking above the mean. Okay, now let's switch gears for a second. This is the percentage that is in the tails. What does in the tails mean? Excuse me, it means if this is my z-score, how much is above it? Okay, now remember, these are all positive scores. So these numbers are just going to be for this tail part. Okay. So that's the area. So occasionally I might ask you, how many people did better than this score? It would be this value. You're looking for what is above. Okay, does that make sense? Okay. Here's a lot more. If I have a z-score of 0.52, okay, again, this is above the mean. My z-score would be somewhere here. I can see that that would be, I would do 50 plus 19.85, okay? The percentage that's in the tail would be this 30.15. Okay, we have several more examples here. All right. This is what I just described, okay? This is 0.5. This is half of the total area, okay? This is my mean, this is my z, this is my tail, okay? A positive z-score means the z-score is above the mean. A negative z-score means the z-score is below the mean. Now, our tables always show this. But does that mean I can't figure this out? No, because it's reciprocal, right? I've got a symmetrical curve, so I can definitely figure it out. So let's practice a few. Okay, so we can use the standard normal table to find the area between the mean and a specific z-score. So if, let's say, somebody scored on the writing, their score was 675, okay? So in order to calculate my z-score, again, I take my score minus the mean divided by the standard deviation. That gives me a z-score of 1.83. Just eyeballing it. Below or above the mean? What do we think?
Above.
Above, right? So see here, above, it's, yeah, good job. So if my mean, right, is 475, or it could also be a z-score of what?
Zero.
0, good. Okay, standard deviation going this way, right? This would be +1, +2, +3. This student scored at 1.83 above the mean. It'd be like somewhere right here. Sorry, guys, I'm not very good at drawing with my mouse, but hopefully this is somewhat legible. All right, so what do I need to do? So I would need to look up 1.83 in column A and find the corresponding area in column B, okay, which would be 0.4664. You can translate a percentage of that, right? That would be 46.64% as the area underneath the curve. So again, let's remember what that is, okay? That is mean to z, okay? It's this area. This is your z equals 0, right? Or your mean. And this is your specific z-score. In this case, it's 1.83. This would give you a score. This is what they're telling you here. It's 0.4664, okay? So that means between those two scores, the area under the curve is 0.4664. Okay, so that's, again, the area between the mean and your z-score. If I take the full picture of that, though, I want to add this section here. I want to make sure I'm not totally skipping ahead. Let me just show you the next slide so that everybody's on the same page. So you say I go, where's 1.83? 1.83 is right here. Okay, so the area under the curve, this is a percentage, okay? This, what I was looking at earlier was a score. So the percentage in this section is 46.64%. Okay, now, if you're like, oh, wow, I don't know, that seems pretty good, right? Out of 100 people, where did the student rank with his massive score here, or her massive score? I would take this area right here, which is 50%, okay? And I would add this 46.64. Out of 100 people, this student would rank 96.64, right? Or 96 or 97. Here's another way I can do it. I know this value is this tail. So the area under the curve from Z on is only 3.36. So I could do 100 minus 3.36. And what do I get? This same number. Okay, it is reciprocal. Questions about that? Making sense? Okay. Here it is again, just with, you know, nicer graphics than Dr. Woltill's little random doodles. Okay, so this is the writing mean, 475. This is what the student got, 675. That represents 46.64% under the curve being 100%. Okay. All right, let's do something a little different. Major bummer, you just open your SAT scores and you realize that maybe college is not in the cards for you. You know your writing score, you got 305. Same mean, same standard deviation. That gives you a score of negative 1.56, which means going away from the curve, right? It's this value right here. You're below the curve. Now, how did I find this number? If all the tables are for above the mean, how did I find this number?
Since they're reciprocal, or since they're like symmetrical, you would just look at the positive 1.56 z-score, and it would be the same percentage.
All right.
I don't know if I described that well, but
no, but you're absolutely right. So you can almost do absolute value, right? You can almost ignore this negative because the table is completely symmetrical. So in fact, let's go back. Oh gosh, I feel silly now. What was the number? 1.56. Okay, now look over here. Now I know this is mean to z if it was positive, but here's 1.56. And the area under the curve is 44.06. Exactly the same. Now here's where I see students make mistakes all the time. They're like, wow, this student is totally doing great. 44% plus the 50, 94, right? What did they forget? This is on the other side of the curve, right? Other side. Okay. So what would be a way for me to identify how this student did? If I'm looking at like out of 100 people, where would you rank? It's not 44, right? So a couple of ways I can do it. Let's go back to our other point. See this percentage and tail? That's really how well he did, or she did, 5.94. Not great, yeah. Okay, another way I could do that. What's the question? Yes. Okay, Hannah, very good. Hannah said, can you do 50, right? Because I know this area, this whole thing, that's 50, right? Because if the whole thing's 100, then half of it is 50. 50 minus 44.06 equals, what is that, 5.94? Is that what it was? Exactly the same. Yep. Isn't it beautiful? There's more ways to get to it. All right. So you can find the area under the curve in the tails the same way, okay? You can calculate, for instance, this score is 2.52. This is very much an error. So in your textbook, it says 5.9. We know that that's not possible. It should be 0.59. Because 2.52, sorry for the whiplash. Let's go back to our, it's not even on the chart. 2.52 is like extreme, extreme, extreme. So little. Okay, what was the other number? 0.92. That's not going to be on the chart either because it starts too high. But in your charts, you can find all of it. You just figure out where is the z-score and then figure out both the area that's under the curve between the mean and the z-score, which would be this area, or between the tail. And remember, everything in your table is going to be above the mean. It's always going to be for a positive z-score. Okay. Now, let's say we want to find the score. So this is the reversing it a little bit. We want to find the score that corresponds to the top 10% of SAT takers. Okay, so I'm doing it reverse. I want to know like top 10%, right? Let's say I'm an admissions counselor and I've decided that's my metric for which I'm going to be accepting students. And I have all their SAT scores and I want to do a filter in Excel to just get the top 10%. So that's who I want to look at. So in order to figure that out, I have to convert my z-scores into raw scores. This is the formula I showed you guys earlier, right? So your raw score equals your z-score times your standard deviation plus your mean. Okay? So if I get to this 10%, I can reverse it, right? I can look in my chart and figure out what is the z number that equates 10% under the curve. In this case, it's 1.28, okay? Now let's see, do I calculate it all for you guys? No, I don't, so let's do it together here. So if x equals z times your standard deviation plus your mean, now I'm hesitating, is that right? Yes, that's right. Plus your mean, okay? What is the z-score for the top 10%?
1.28.
1.28, okay? Who remembers what was the standard deviation of this writing for the SAT? $109. Okay, now order of operations. You are doing this first and then adding the mean. What is the mean? The mean, you're right there, Aaron. The z-score of the mean is 0. What is the raw score of the mean? Because I'm switching it back to a raw score. Hopefully everyone sees that is 475, okay? This is my mean right here. Okay, so what is my score for X? I multiply those values. So
I got like
what's that?
614.52.
Sorry, I didn't hear that. You got what?
I got like 614.52.
Okay, so yeah, that sounds very close. So 1.28 times 109 plus 475, 614. I almost just went and typed it, that doesn't work. 614.52. Because it's an SAT score, I think it is a round number only. So that's why that rounds to 615, which is what we see right here. Okay. All right. Now I want all of you guys to calculate this next one. What is the cutoff score for the lowest 5% of scores? Okay. So I have some values here that I know. I don't know Z. I'll give that to you in a second. So this is Z. What's my standard deviation?
Is it still 109?
Yep, still 109. Okay. Plus the mean. Whoops. What is my mean?
$475.
475. Now, again, I highly recommend that you guys draw it out. What is it we're looking for here? I'm looking for the bottom 5% of scores. So if this is my mean, right? What is the area that I'm really looking for?
Wouldn't it be like that close to like back tail area then if it's the lowest 5 scores?
Absolutely. It's going to be this little tiny section right here. So this is the bottom 5%. Okay. If you had your appendix in front of you, you would look through the values and find the one that the area under the curve between Z and the tail equals 5%. Okay, now you don't have that in front of you, so I'm just gonna give it to you. It is negative 1.65. Okay. Now you plug that in. What number should we get?
Got a 295.
That's right. Let's see somebody else. Hannah, way to be on it too. Yep, 295. I got 295.15, but again, it's the SAT score, so it'll just be a flat 295. Yep, you're on it, Lainey. Okay, so I can double check my work too, because now let's say I forgot to put the negative number on my calculator and I got instead like a number in the 600s. I could go back and see, wait a minute, it's asking me from bottom 5%, what are the chances that my number is going to be 600, which is clearly above the mean? It's very unlikely. So something went awry with my math, okay? So as soon as you see 295, yep, it is much smaller than my mean by almost 2 standard deviation. Yep, that tracks. And here it is visually represented in a much cleaner way. That is the bottom 5% at a z-score of negative 1.65. Okay. Now, finding percentile ranks for a score that is higher than the mean. If I get this score, again, 680, I can figure out what is the area underneath the curve. It'll be for this area, plus 50, right? So this tells me that's 47. Or I can look at what is the area between Z and the rest of the tail, which would be 3%. So I'd be able to say that this individual who scored a 680 scored in the 97th percentile. So really the z-score, assume that it's out of 100 because the totality of it is 100 if you're doing it in percentages. Okay, same thing. If this score shows 380, right, I can calculate that the area underneath the curve, this was likely 30%. I add 30% plus 50, that gives me 80. So there's a leftover 20%. So that is the 20th percentile. Okay, you can flip those numbers around. This student performed at the 20th percentile, or 80% of students performed better than this student. Okay, that would be, you could flip it around, the same thing. They're the same statement, really, just flipping the numbers in terms of how you're representing it. Okay, this student scored a 655. The area underneath the curve here from Z to the end is 5%. So I know that student scored in the 95th percentile. Okay, I'm kind of repeating myself here, but I want to make sure this all is making sense. Okay, this is a score that's actually quite close to the mean, 448. It's a small difference. Now this one, the area under the curve is probably like 10%, okay? But the way you can flip that over is that the student scored in the 40th percentile, or 60% of students scored better than this student. Okay. This is more data. If you guys want to practice, you can take a look. This is a specific research that looked at standardized reading and math scores for children with a variety of conditions. You can see here, no health condition, low birth weight. If they were exposed to smoking, that was medium versus heavy, and what condition they may have had at age 7 versus 7, 11, and 16, okay? you see here the mean reading z-scores, and this is what's so powerful, you guys, because your reading score at age 7 and again at age 11 and 16, those are going to be hugely different numbers. And if you didn't have a way to standardize it, you wouldn't be able to compare it and make any sort of meaningful interpretation from it, right? So same thing, you wouldn't really be able to compare reading from, you know, if you're looking at math z-score, you know, how do you compare those? They're going to be on totally different scales. But as soon as you have a z-score, then you're able to compare them more meaningfully. Okay. All right, quick review. We talked about the normal distribution and what it looked like. We talked about the standard normal distribution and where to find it in your textbook as the standard normal table. And we talked about what is a standard z-score. Lots and lots of information tonight on top of the lab. Questions that you have for me to help clarify this information? How can I help?
I have a question about the lab. When you pulled it up earlier, it said it was due on Monday, March 1st. Is that, it said like Monday, March 1st at midnight. Is that right, or is it due like on the day of class?
It's definitely wrong. Oh, this thing. Keep. Oh gosh, your face disappeared. Here you are. I am, okay, let me look at it. So when they created this class, they just copied everything over from fall semester. And so it kept some weird random due dates, and looks like that's one of them. So let me edit the settings. Sure does. So I'm going to take off, hopefully now there's no due date. You guys just know that it's due next week, but it'll allow you to submit it now if you wanted to, because sometimes it gets finicky. It won't allow you guys to submit early. I don't know why it would care and do that, but yeah, so you should be good to go now.
Thank you.
Yeah, great question, Liz. Thank you. Any other questions? Okay, that was a lot of information. We're going to do more z-scores next week. We're going to practice it more. Again, I am not joking when I say, here, let me share my screen real quick again. Just don't judge how many windows I have open. Whoop, I don't know why that's a Zoom. What is happening? Z-score distribution. Okay, table. Boom. You guys see that? All of these lovely tables. The data is all the same, right? The numbers don't change. They're all the same. It's just whichever one looks easiest to follow, right? Like this is very similar to your textbook, okay? That's from the mean to your z-score. So this one does not include one that's from the tail to z, but like this one does. And this one, oddly enough, does it on the negative, which is weird. I don't usually see that. It's usually always positive. But again, you can use this exact same chart, just ignore the negative, right? And make sure that you think it through when you do the math. Okay, so this was all so you could see, don't panic if you don't have the appendix. You have access to it at your fingertips, on your phone, anywhere you have access to the internet. All right, any other questions? Okay, that's what I've got for you. This was meaty and we didn't even take a break. So, all right, enjoy the rest of your evening, you guys, and then I will see you all next week. Remember to submit your lab 1 if you've not done so already, and then lab 2 is due next week.
Bye. Thank you.
Thank
No
you.
problem.
Thank you.
Have a great night, you guys.
Bye.
Have a great